Welcome, everyone. Thanks so much for joining us. This is the PLOS Synthetic Biology Community Google chat with Dr. Rob Carlson. So it's great to have everyone here watching. Sorry about the delay. My name is David Schifrin. I'm the community editor of the PLOS Synthetic Biology site. And also on this chat is Akriti Jain, who's my fellow community editor. And she will be managing the Twitter feed for this. So our handle for that is @PLOSSynBio. That's all one word. Be sure to include the hashtag #CarlsonLive. And with that, let me introduce our guest today, who is Dr. Rob Carlson. Dr. Carlson has really a remarkable history in many aspects of science. He earned a doctorate in physics from Princeton University in '97, followed by a research fellowship at the Molecular Science Institute in Berkeley. After that, from 2002 to 2007, he was a senior scientist in the electrical engineering department at the University of Washington. And from 2003 to 2008, he provided technology analysis and strategic consulting as part of the Bioeconomic Research Associates. And in this role, he wrote extensively on pandemic preparedness, synthetic vaccines, biofuels, biological technologies, and provided insight and analysis to both corporations and governments around the world. So his scientific work has included extensive work in microfluidics, among other things, and Dr. Carlson has also developed a number of new technical and economic metrics for measuring the progress of biological techniques. He is the author of the award-winning book, Biology is Technology, The Promise, Peril, and New Business of Engineering Life, which was published in 2010 by Harvard University Press. He's also an advisor and consultant, serving as a principal at Biodesic, and most recently he helped found and serves as the managing director of Bioeconomy Capital, which he'll be talking about more here in a few minutes. So Dr. Carlson can also be found online at synthesis.cc and on Twitter at Rob_Carlson, and that's all lowercase. So Dr. Carlson, thank you so much for joining us today, and I'd love to have you just give a little bit of background on your work and your history.
Well, thanks for that introduction, and thanks for having me on. I look forward to the chat. I'm basically just interested in how humans are going to use biology as a technology as we go forward, how we get our food, water, land, all from biology, how we reuse land with biology. Increasingly, we'll generate chemicals and fuels from biology, and the fuels story is going to be long and complicated, but more and more fuels are going to come from biology over the years. I'm interested in security. I'm interested in how we proceed safely and securely. Everybody wants safety and security, I think, but that doesn't mean we start with fear, which is where the conversation also often starts, and so that's what I spend a lot of my time working on. Of late, I've become ever more interested in where we get our stuff from. So I started in very much an academic physics environment, working in basic physics and biology problems. And over the years, I've just really become more interested in how humans produce stuff, and the way the economy works, and where we get stuff. And as we learn to better control biological systems, then we will get more of our stuff from biology. So that's what I'm working on most directly at the moment.
Great. So tell us, if you would, a little bit more about these new projects that you've got going on, Bioeconomy Capital, and what role you want to play in the bioeconomy.
I think part of it is that I'm just ready to build stuff. I've built stuff in labs before. I built small things. I built instruments. I built a few genetic circuits here and there. I built molecules. And I think I'm ready to go ahead and build bigger things. I built small companies. I built consulting firms. I'm ready to work on bigger projects. And maybe we should take a step back and think about what the bioeconomy is for a minute, and why it's important. So usually when you hear biotechnology, people think of drugs or crops, and those are both big, but each of them is only about a third of the total pie. The other big piece is industrial products, industrial biotechnology. That's fuels, enzymes, and materials. And all three of those areas are growing very rapidly, and together they constitute more than 2% of our GDP at this point, as best I can tell. And that's a story that maybe we should talk about too. It's actually very difficult to measure this. We measure it the rest of our economy very well. We don't measure biotechnology very well. So those estimates are very hard to come by. But nonetheless, it looks like I said, a bit north of 2% of GDP, and on an annual basis, biotechnology is producing something like 6% of our GDP growth, which is a big number. So how do we do that better? How do we more efficiently produce stuff? How do we get past the bottlenecks? I mean, a traditional or long-standing problem in getting from the lab to the to any consumer product or a drug or a fuel, whatever it is that it's not so hard to show progress in the lab, but scaling it up is very difficult to get into commercial markets. So that's one of the problems that we are attacking head-on with Bioeconomy Capital, is trying to identify bottlenecks, identify slow spots, identify places where most of the cost is. So for many years, I tracked the cost of DNA sequencing and synthesis and the productivity of those activities, and that was critically important economically for a while, because both of those were very expensive. Reading and writing DNA was very expensive and very hard to come by for quite a long time. But now it's not. That's not where most of the cost is. So we're focusing on the other part of the problem. How do you get, once you produce an organism, built an organism that can make something that has value or that somebody wants, or is a drug or whatever it is, how do you make enough of that to make it commercially viable? And I take inspiration from brewing beer, actually, in this case, which is biological manufacturing. It's distributed biological manufacturing, in that microbrewing works everywhere. It works at all scales, technically and economically. And the more we can harness something like fermentation to make stuff that's even further away from water than beer is. So beer is about $1 a liter, or a few dollars a liter in terms of its cost. It's usually more than gasoline, actually. The further we get away from that kind of a product to something that's worth $10 a liter or $100 a liter, the more easily that distributed manufacturing base works, the more easily it scales. So we're investing in working with companies anyway, and then investing in technologies that enable more rapid scaling, that enable precision biology, enable tighter engineering bounds up front, so that you can more easily get to the market, basically.
Okay. So how do you deal with the issues of luck when it comes to scalability? You talk about this a bit in your book, that a lot of times in science we stumble on things that make things better, but because we don't have a full comprehensive view on how every biological system or pathway works, sometimes we just have to rely on hoping things work out. So how are the companies that you're working with, and how do you think about engineering this more specifically? You talked about the engineering constraints to get more focused on managing that luck.
Well, we're trying to take the luck out of manufacturing, actually, the luck out of scaling up. So luck plays a very important role in science, or serendipity, or mistakes even. Everyone has made a mistake in the lab that turned out to lead to an actual result. And that's fine, that's great, that's the way science should work, and does work. You just can't get away from that. But when it comes to building stuff that has predictable behavior for the economy, right? You don't want luck involved in building your airplane. You don't want luck involved in building your iPhone. You also don't want luck involved in building an organism that makes a drug, or that makes a crop, or that makes whatever it is that you're interested in. Or maybe you're going to grow a house. You don't want luck in growing the house. You want that to be very predictable, and you want it to be understandable. And so what we're trying to do is invest in companies, work with companies that can bring technologies, develop technologies from scratch, or bring other technologies in from outside of biology that enable the variability to be removed from much of the manufacturing process, and make it a more predictable, more expedient process to get from a demonstration in the lab, where luck may have been important, to a demonstration in the economy, where you don't want luck to be anywhere near what you're doing.
Okay. What are some of the tools that you see having come out in the last, let's say, 10, 15 years that have begun enabling this process in these companies you're working with?
Well, there's a great deal of conversation now about reproducibility in science, and so that's where start the conversation. But that reproducibility issue extends all throughout manufacturing. It's getting rid of the luck. It's getting rid of the variability that plagues the transition to commercialization. So the scientific side of that story, if you go back a few years, there was a paper from Amgen published in Nature Biotechnology, and another from Bayer Healthcare, where Bayer first attempted to reproduce its own internal results in the lab and could only reproduce about 25% of those. And Amgen reached out into the peer-reviewed literature to find papers in oncology, and they could only reproduce roughly 11% of those papers. So if that's a general result, and anybody who's worked in the lab knows that reproducibility can be a challenge, especially in biology. Charitably, half maybe of the work that's published in peer-reviewed journals might be irreproducible. It could be more than that. It could be 75%. It could be 90% if the Amgen result holds more widely across biology. So that speaks of it doesn't mean those results are wrong first. It just means they're irreproducible, or it's hard to reproduce them. And that, in effect, means much of that work is not very useful to anybody else. So what you want to do is make not just the science reproducible, but also the communication of the methods reproducible. And again, there's so many anecdotes out there of two teams not being able to reproduce each other's results, and they get together and they work on it, doesn't work, and finally, you notice that one of the teams, one person handles a pipette a particular way, or the temperature of a water bath is off from what it was thought to be, or they picked their nose that day, or whatever it was. It's humidity in the lab. I learned about a great story from Rosetta the other day where they had had their array process working extremely well. They moved into new facilities that were in different places and had all kinds of crazy variability that they didn't expect in their arrays. And it turns out that eventually they noticed a diurnal cycle. Eventually someone realized that they had moved from a relatively isolated building to buildings that were near freeways. So they were seeing a traffic effect. And then months go by, and eventually they start to measure things in the lab and realize that they're seeing an ozone effect, parts per million ozone effect. And that's the kind of variability that, even though they had a commercial process worked out really well, transferring it to a new location introduced something that no one had seen before. So I'm not saying that we're automatically going to be able to identify those kinds of signals quicker, but at least we can identify that that's the problem quicker, right? If you have a software tool that helps you move the technology from the bench to the commercial side, or just helps you communicate between laboratories. I'm quite excited about Antha and other languages like that allow you to reduce English language protocols to software. So Antha is a language written by or developed by Synthase in the UK. We've invested in Synthase. That wrangles robots first. So Synthase and companies like it are very heavily dependent on automation, and they need a way to rapidly control many robots with high precision throughout the lab. So they developed Antha in part to get that done. But it also enables them to communicate protocols and reproduce their results more easily. So Antha is an open source language. Anyone can develop, anyone can use it. And what it's going to allow you to do is take the shelf of current protocols in molecular biology that's written in English language and reduce it to instructions for scripts for robots. And there are always going to be things, at least in the near term, that humans have to do. Not everything in the lab has a form factor that a robot can take care of. There are some things that a human is always going to have to do, probably. But many of the things, moving fluids around, pipetting robots, PCR, all that stuff, where we know that variability can come in at every step, the more we can bring automation in to reduce that variability, the better the result, the easier it is to communicate, both on the scientific side, as part of publication, as part of sharing those results, and then also on the commercialization side, because once you get the protocol figured out in one lab, it ought to be easier, bit of a hypothesis, I suppose, that we're going to test, it ought to be easier to move that protocol someplace else. If the protocol is implemented by robots, and the robots are the same everywhere. We're still going to have, ozone issues like Rosetta did. We're still going to have temperature. We're still going to have humidity. There's still going to be funny variations in reagents and shipping and all those sorts of things. But ironing those out, identifying them, is a big part of the process.
Okay. So kind of dovetailing off of that, with kind of the advent of combining engineering with biology, and now programs like iGEM and this real push to standardize the parts and to standardize the processes, get the protocols put together, use robots. What do you see happening as far as kind of the upcoming generation of scientists? So Akriti is an iGEM participant, and how do you see that events like that shifting how scientists are thinking about their work, and where do you see that going?
Well, among the things that's going to happen, let me throw out a few more examples of companies I see that are making things that are going to facilitate this transition or be part of the transition. So Tim Gardner, who helped develop a highly automated system at Amyris Biotech, that took a process that was suffering from all kinds of variability and lacked precision, to turn it into a very high precision operation, where as they dialed in the error bars, they understood the error bars in their measurement process, they understood the impact of those error bars on the productivity of making stuff with their bugs. Their productivity went through the roof, and now they're commercially viable precisely because they dialed in those error bars, they understood those processes. And he is, extracting that knowledge, building another platform at a company called Riffin to enable anybody to design experiments, think about data in the way that he learned was very useful at Amyris. We're going to have cheap robots, cheap instrumentation come in. A company called Opentrons is building, you've probably seen this, they had a Kickstarter for an open source lab robot, open source fluid handling bot, pipetting bot. There's OpenPCR with from Chai Bio, which is going to be a qPCR box, and Opentrons now is talking to Chai Bio to see if they can interface those two boxes. So what we have is less expensive hardware coming in. We'll see if the engineering of these boxes works out, if we actually can get the precision we need out of automation that's low cost. But that's coming in, and what that's going to do in combination with Antha or other software platforms is enable people who don't necessarily have as much experience at the bench to program biology. So if you know how to code, if you know how to wrangle robots, if you know how to think about scripting languages, then when that shelf of current protocols in molecular biology becomes a list of scripts that you just click on and order to make stuff happen, many more people are going to be enabled to build stuff in the lab. And among the first protocols that Synthase is working on, and Opentrons and others are working on, are DNA assembly protocols. So if you need a genetic circuit, right now there's a lot of hand pipetting. It's either that or you order it out and you wait a while and hope someone can deliver the genetic circuit that you need. But there are protocols out there that are very high efficiency that can be automated, and those are coming. So, again, another hypothesis. We'll see whether putting those in the hands of people are going to make a difference. And when it comes to iGEM, now as the robots become more prevalent, as people, as kids, as students learn how to handle biology in a way that I never had a chance to, right? This is not something that was, let's see, it's just over 10 years old, right? So that's not so long. But there are 25,000 iGEM alumni at this point, something like that. And they've all been exposed to the idea, anyway, of biology as plug-and-play parts. The reality, of course, is that they all stumble over the fact that biology doesn't consist of plug-and-play parts. It's going to be a while before we have that set of parts, and it's going to be a while before we build up a collection of parts that are predictable, that are understandable, and that can be composed to build systems whose behavior can also be predicted, and then build organisms whose behavior can be predicted. I mean, it's not going to be a quick process. We didn't go from the Wright Flyer to the 777 in 10 years. That took a century. And we did it not by adopting parts from things that flew, right? The airplanes we fly around in don't flap their wings, and the reason is we don't understand how birds work to this day, and we can't build a bird, we can't build an object that flies like a bird, except in very special circumstances. Now, it's not a general technology by any means, but what we did do instead was build parts, build systems whose behavior we could predict, and we rely on those very heavily, right? There's no luck, again, in getting on a 787 or a 777 today. There's bad luck if something goes wrong, if a person makes a mistake, or if there's weather or whatnot. But the airplane itself is usually not at fault. The engineering process is not at fault. Those are very predictable systems. And now many thousands of undergraduates and graduate students around the world have been exposed to the idea that you can maybe do the same thing with biology. And there are an increasing number of examples where that is explicitly true, where people have said, here's a mathematical model for how this biological system ought to work. We're going to use these parts, stick them in an organism, and see if our model is correct. And increasingly, that happens. That works. Again, it's not general yet. The number of parts you can do that with is fairly small. But nonetheless, there's a fair amount of hope there, I think. And so over time, we're going to have more students coming in from electrical engineering, from computer science, from physics, from wherever it is, who understand, who've been programming, I guess, building bots, building drones, whatever it is, building objects that follow instructions for many years. And now they're going to have the opportunity to apply those skills to building biological systems. And that's going to be very interesting.
Very cool. Yeah, I think it's an exciting thing, looking at how over time, as scientists have become more and more specialized in their own field, there's now getting to be more and more collaboration across disciplines, bringing biologists and biochemists together with the programmers and the engineers. And so I'm excited to see where that goes. Going back to what you were talking about flight, and we're early on in this process, and so if we are in the, let's call it the 1885 to 1920 range equivalent in synthetic biology, there are all kinds of concerns about biosecurity and risk, and what happens when smallpox gets out because a TV show had a terrorist who got his hands on an old bone that was infected, and now people are worried about this, and that leads to debates on Capitol Hill and elsewhere. So how can we as scientists respond to the concerns as we are developing this technology and figuring out where to go?
That is a question I wrestle with every day. So the first answer is all you can do is tell the truth. All you can do is explain what you know about science and try to communicate the world that you understand, and when possible, try to correct misconceptions. One of the challenges, of course, is that there are others who rely on misconceptions to muddy the waters or to make money. I was just listening this morning to a report on the ways the media got Ebola wrong.
In many ways.
I have to think that in at least some cases that was intentional, right? There was information out there, there were facts to be had, and in at least some cases the media clearly just ignored those facts and made up something else because it was a better story. Or had somebody on who was willing to say whatever came into their head, or was willing to promulgate fear instead of facts. And that's a challenge constantly. That's part of democracy and free speech. So what do you do about that? All you do is work with it, work around it when you can. So that's one kind of conversation. That fear is a tool just as much as facts are a tool, and some people use fear rather than facts. That's the world we live in, and maybe that's just part of dealing with other humans. But then there are more substantive issues, real issues about safety and security, and the world that we're looking to is a world that we will be building. We're not talking about biology as we find it. We're talking about biology as we will build it. And right now it's extremely difficult to build much of anything. It's getting easier to build things. The automation is going to help. The work on precision is going to help. But the idea that anybody can go into their garage and make a pathogen just isn't very realistic. And yet, we have people who stand up in public and people in the media who stand up and say the intersection of synthetic biology and garages and DIRC, dual-use research of concern, is going to lead to Armageddon. We're going to have a bug that kills everybody come out of a garage. I had a lab in my garage, and I will testify that it is extraordinarily difficult to get anything to work in a rudimentary environment. You can build a more complex environment, you can spend money, you can invest, etc. But maybe it helps to think about this as product development. It's not that hard to get something to work once again. It's really hard to get something to work generally. And the idea that in a garage you're going to go directly from it worked once to anything that is truly problematic is just a stretch in my experience, which is not to say that it can't happen, but it's hard. And much of the fear is based on the assumption that it's not hard, and that's just not realistic.
If you don't mind, just to follow up on that, can you recount the story in your book about, I don't have the first name written down, but the Randerson story about ordering parts of the sequence and your conclusions from that? Because I think that fits in nicely with this discussion.
Right. Well, so the background here is that in 2004, 5, 6, somewhere in there, there was a great hue and cry about access to synthetic DNA. So if you want to build a biological system, generally you need DNA from somewhere. And the idea was that the fear, and I will say that, having to think through this once, I was concerned too for a while. The idea that you could build a pathogen from scratch is not something that we should be dismissive about. We ought to figure out how hard it is. We ought to figure out how realistic that is as a problem. So this conversation is going on. There are discussions in public and behind many closed doors about whether or not to regulate synthetic DNA, how to track people who order synthetic DNA, how to track what they order, how to figure out if what they order can be used to build something bad. And then into this conversation steps James Randerson, who was a reporter with The Guardian. And he took it on himself to try to order oligos, little bits of DNA that from the smallpox genome, or that would code for bits of the smallpox genome. And he successfully did that and had them sent to a residential London address and made a big deal out of it. But of course, you couldn't do anything with those little bits of DNA. For that to be a threat, you would have had to have all the rest of the DNA, or have a similar genome at your disposal and be able to combine the new parts with the old parts, which at that time was not something that was trivial to do, and I would argue today is still not trivial. And he raised the stink and asserted that it was easy to do, that it was a threat, and that something must be done immediately. And I think I responded with a haiku on my blog that basically he was just setting his hair afire in order to draw attention to himself. Because what he made very clear was that you couldn't actually get anything done, right? He ordered these parts, and that's as far as it went. He would have had a hard time getting any further. And those kinds of conversations continue to this day. Whether it's about the flu or it's about Ebola or whatever it is, people continue to assert that it's trivial to order bits of DNA and bring them into a facility and assemble a pathogen and have that pathogen be problematic and infectious and deadly, and et cetera, et cetera. So we must regulate synthetic biology, goes the argument. We must regulate the tools, we must regulate the people, we must somehow keep track of all this. And I'm not dismissing all these concerns as baseless. I'm really saying we should evaluate the risk of each of those things and see how hard it is and see what the risk actually is. And most of the time, the public conversation ignores that aspect, right? The reporter will stand up and say, this is very easy, look, this is a very simple thing I did, ergo, the complicated thing is easy too. But it's not. So that's a conversation, again, I wind up in, not necessarily on a daily basis, but a weekly basis or a monthly basis. There are always people who are concerned about that. And we should be concerned about it, frankly, right? We need to keep track of these technologies. We need to understand how threats can evolve, where they can come from, this pace at which they can evolve. But that doesn't mean that there are immediate threats, right? They're impending threats maybe, but they're not imminent threats. And so we should keep that as part of our understanding of the way the world works today, as opposed to the way the world might work in 10 years or 20 years, something like that.
Continual evaluation. Okay. All right, I'm going to switch tracks just a bit here, and we just got a question from Henry Holbrook on through the Google Q&A app. So the question is: it seems like biotechnology is largely dominated by those with advanced degrees, while the software hacker culture is nearly the opposite. Do you think the growing bioeconomy will see a decrease in the educational barrier to entry to doing biology? And I think we kind of started to touch on this with DIY bio and the blending of the fields, but I think it's a great question.
Well, let's just look at iGEM first. Right? So when iGEM started, the initial teams were producing Nature and Science papers within a couple of years, and they were working on projects that they're working on projects that when iGEM started, a team of PhDs wouldn't have thought to try, or would not have been capable of pulling off, or if so, only with great effort. Right. So that alone is demonstration that the world is changing very rapidly. Tools are proliferating, skills are proliferating, people have access, and it's not just curiosity that's driving this, it is economics that's driving this, right? The US, the UK, there are, I think, about 20 countries around the world that have explicit economic policies that identify biotechnology and in some cases synthetic biology as important technologies for the future. We just had introduced into the US Congress yesterday, or at least announced a draft bill to build a federal engineering biology research program, which is quite remarkable. The UK has announced somewhere in the neighborhood of 250 million pounds now that's dedicated to research and commercialization of synthetic biology. So the pull is the market. The pull is more biology making more stuff, more places in our economy. And the engineering tools are definitely getting better. And I think the challenge we face as far as the number of people who have access is making sure that they all understand the power at their disposal while not getting overwrought about fear, not getting overwrought about the potential for harm when that may not be the most pressing problem, right? It can be very hard to get anything working in the lab, and then it can be very hard to transition whatever that thing is to working in a context outside the lab. And that's the basic challenge at the moment. So yes, skills are the skill level is coming down. As I said, we're going to have people who know how to wrangle robots who are going to make an impact in biology in a way that they couldn't have done just a few years ago. And that's because technology is changing, technology is evolving, and it isn't just in biology. The robots are getting cheaper, microcontrollers are getting cheaper, so there are other economic and technical phenomena that are transpiring that are coming together to make biology easier to engineer, or at least to manipulate, and hopefully we'll be able to call it engineering in the same way as we engineer bridges and airplanes and cell phones someday soon. We're not there yet.
So as a follow-up to that, this is kind of a multi-part question, but what would you say first to somebody who's thinking, what, this is, the tools are coming online, the barriers to entry are coming down, I want to set up a lab in my garage or go to a biohack space and do some biology and put some pieces together. How would you encourage them, both as a scientist and as somebody on the finance side? And then also kind of the second part of that is how should the scientific community as a whole be encouraging the general public to be getting involved in these types of projects?
Great questions. So the first thing is, hooray, go do that, learn a lot. You're going to make a huge number of mistakes, but that's the way you learn, right? You're going to drop stuff on the floor, you're going to spend a week mixing stuff, and then realize in that final step before you get your data that you're not sure you put the right clear liquid in the other clear liquid, and maybe you got the tubes backwards, and you're going to go nuts. Fantastic, you should do that. That's what molecular biologists and bioengineers and iGEM students do every day. That's the reality right now of trying to make anything work in biology. And that's the only way you can learn, is by trying to build stuff, trying to make it work, trying to do experiments. You know, I had a lab in my garage at a time when that was sort of a dicey thing to do in the United States. The FBI was arresting people for doing that, even though it was entirely legal. There was some misunderstanding and some apprehension and some overreaction. It's very different today. The FBI is now reaching out. There's an outreach program to community labs and to DIY bio and biohackers of all sorts to engage rather than to try to shut it down. And I think that's the only approach that makes any sense. I don't think it's feasible to try to control this technology. We could talk more about that if you like in a moment.
Yeah, absolutely.
And we need more of that activity to create more startups, right? So if you look at where we get our new stuff in the United States, it's garages and small entrepreneurial organizations. There's a list in my book and online of technologies that went through garages at some point in their development cycle, and it's A to Z, literally everything in our economy, except for nuclear weapons, thankfully, power. And there are reasons why nuclear power is different than, and nuclear weapons are different than other kinds of technologies, and that has to do with cost, it has to do with difficulty, it has to do with scale, it has to do with power consumption, all kinds of reasons why it's different, and I think that's important, right? So biology looks a lot more like the technologies that have successfully gone through garages and are very difficult to regulate than it does like, then it looks like nuclear power or nuclear weapons, nuclear anything, really. And that's instructive for thinking about how we should approach security and safety in biology, I would suggest. Again, we can come back to that. But then on the startup side, right, you need a place to work. I have been talking to the White House and now the governor's office here in Washington State about startup spaces, about how to encourage DIY bioactivity that is safe and secure. And I think a way to do that, a pitch I'll make here today, is that every big city needs a hackerspace where you can go do biology. And that's not just for education, although that's important, right? We need places where people can learn about biology. We need places where kids can do experiments, learn everything from microscopy and dissecting brains to how to build a glowing bug, or maybe try to make something that makes a biofuel. Who knows? We need those spaces. We need that education. But we also need some rudimentary infrastructure for startups. You don't need a lot. You know, a biology startup doesn't actually need an expensive lab with lots of expensive cabinets. You need a room with a drain in the floor and a sink along the wall and a bunch of power outlets, and that's about it. But that's an important bit of space and infrastructure to have, especially one that's blessed by local or state or national authorities, whatever it is. Yes, you come here, you do the work here, we're happy to have you. You know, it's a place to receive shipments, which is not always an easy thing to do. You need reagents. You probably need a freezer at this place. It doesn't have to be a fancy freezer. Just need a freezer there to keep reagents fresh, and maybe a refrigerator. And then on the capital side, you know, I struggled with this for a long time. I wasn't, and my partners, none of us have been particularly enthusiastic about our own experiences with investment capital over the last 20 years. And so all I can say is we're bringing our experiences to our new endeavor, right? We're trying to work with entrepreneurs first and write checks. We're not just writing checks. The point of Bioeconomy Capital is not merely to be a source of funds. It's to engage with people and bring our experience and strategy and building and shipping hardware and mashing molecules and building big companies. It's to bring that experience to more people, to startups, and particularly where we see the bottlenecks again in getting stuff done in the lab and then moved out into the economy. I think we need more flexible capital for smaller businesses. And I think the best way to encourage startups is a space like I described before. So there's a document somewhere on the web that I wrote some years ago called Public-Private Partnerships for Developing the Bioeconomy or something like that. It's on my website somewhere on synthesis.cc. That looks at all these issues, looks at how we get our stuff, looks at safety and security, and I think we should have spaces where people can go learn. I'm not saying we should try to control people's activities elsewhere. If you want to build a lab in your house, you can always do that. It's always going to be almost impossible to prevent people from building labs wherever they want to build them. Mm-hmm. But wouldn't it be a lot better if we could engage people, do things together, have teams collaborating, building projects in more collaborative spaces? So I'm on the board of DIYbio.org, and also I'm on the board of the local Seattle Community Lab, which is called Hive Bio. And in both those contexts, I'm very much have an eye to how do we create a space and create a community where people can be both safe and secure and get something done. Ultimately, though, it is do-it-yourself, right? There's this conversation that people have about do-it-yourself or do-it-together. And I think that it is important to be able to do things together. I think that there's a lot to be said there for building that community, but ultimately it comes down to the individuals who are doing it themselves and their understanding of the technology, the understanding of safety, of even disposing of chemicals in the lab, right? That's another reason to have a centralized facility because hopefully people aren't using reagents that are too nasty, but sometimes you need ethidium bromide or whatever it is. And you want to make sure it gets disposed of safely. So having some kind of central location where that information is available and the infrastructure is there to handle it would be a fantastic step forward.
Okay. What do you see from the academic side? Are academic institutions supporting these kinds of efforts? And how can they do that? What's the interaction with the university?
Well, certainly from iGEM, from the perspective of iGEM, there are hundreds of universities, or I guess 150, 160, something like that now around the world, who are supporting those teams or enabling those teams in some way. So that's fantastic. When it comes to commercialization, I'm not as keen on what I'm seeing. It was a study done by the Small Business Administration in the U.S. that the economic value add of university technology transfer offices, and the news wasn't so great. They weren't all doing a very good job of moving stuff out into the commercial world, yep. And more often than not, they were just kind of supporting themselves rather than generating value, either for startups or for the university. And I would certainly like to see a better transfer of work that's done in universities out into the commercial world. I don't really want to get into Bi-Dole and its impacts here, but I think that needs revisiting. A lot of people are really excited about what that's done for commercialization, and I'm really not excited about what that's done for commercialization. I think that it created a lot of expectations about using intellectual property from universities as a source of revenue generation, and it's not worked out that way, and I think, in general anyway, it's not worked out that way, and I think we should, again, revisit that. I think we ought to have more community involvement between universities and people who are interested in biology. I'd love to see big universities in big cities anywhere in the world host the startup space. That costs money. It takes resources, it takes space, it takes time, but nonetheless, what a great way to get engagement between university and the community. I would love to see more of that.
Okay. Yeah, just anecdotally, I have a number of friends from various institutions who have been working to license things that they did in the lab, and it's not trivial. We'll just say that. So, just a couple minutes left here. If you don't mind, I would love to go back to what you had mentioned about controlling technology and kind of how the FBI, other agencies have been responding to that. I just wanted to follow up on that and get your thoughts there. And then I've got just one or two other questions, and we can wrap it up.
Well, my thinking about this goes back quite a long time, and trying to understand what security would look like in a world where we did have control over biology. And now I'm going back 15 years or more to, me thinking out decades, trying to build a picture, tell the story for myself that made some sort of sense. And where I started with that was looking at analogous technologies. And an obvious thing to look at is illicit drug production and distribution. And methamphetamines are a prime example there. Building organisms is certainly harder than making methamphetamines, but it's the same scale, it's the same kind of labor, it's the same kind of physical infrastructure, pretty much. And if you go back and look at our experience with methamphetamines, it's not so great. The enforcement activities that the U.S. government has put in place to try to control the production and distribution haven't actually impacted use very much, and they have, according to the DEA's own internal reporting, created bigger, blacker markets. So they incentivized what they call professional drug trafficking organizations, DTOs, that are better at manufacturing and better at distribution. And that isn't what you want to do with biology, right? You don't want to create a security structure that makes the problem worse. 2000, I guess, roughly 2003, I published my first paper on the security issues here in 2003. And it was very rapidly involved in conversations where people were saying there won't ever be a black market for DNA. What are you talking about? This is ridiculous. It's unrealistic. Well, it looks like we already have at least a gray market for synthetic DNA, if not possibly a black market. It's not black only because there aren't regulations in place to restrict access to DNA, but the screening programs that were stood up to discourage certain uses of synthetic DNA and discourage certain parties from receiving synthetic DNA have incentivized commercial activity to go right around the screening activity. And so that was predictable, and in fact, I said that would happen. And to have the security community shift from that's ridiculous to, oh wait, I see that that's a problem and we need to engage rather than discourage, is a great shift over the last 15 years. So you can look at other kinds of technologies too, software, everything from handbags to drones to, look at Alibaba. It's filled with products that are not exactly on label, I guess. All kinds of copies, all kinds of pirated things, all kinds of stuff that's gone out the back door of the factory instead of the front door of the factory. We should expect the future biology to look just like the way everything else works. There's no reason I can come up with that biology might be different than all the other technologies we have access to. It may be more powerful in some respects, but as far as the economics go, as far as the desire of people to use it in various ways, they're going to use it just like they have everything else. We can look at 3D printing. That story is early, right? But already we're getting 3D printed guns or parts of guns. We're getting other components for other kinds of nefarious devices being printed. And the idea that you can either control the hardware or the software or the products doesn't make any sense. It's already very difficult to do. It's only going to get worse. Biology looks a lot more like that than it does like big buildings and anything that you might secure with guns, gates, and guards, as the phrase goes. So, I've been accused by some of eschewing radical openness, and I guess that's what I want to see. I want to see more information. I want to see more education. I want to see as many people as possible who understand both the opportunities and the risks as they develop. And in particular, I want to have more people understand how hard it is. It's not the case that you stroll into a lab and you magically create something that's either good or something that's nefarious. It takes a hell of a lot of work. And so we're early on, right? And we can learn from other kinds of technologies. We can learn from other kinds of successful engagements between regulatory authorities and technology, and unsuccessful engagements between law enforcement or regulatory authorities and technologies. And I'd like us not to screw it up.
Great. All right. Well, just one final question, if I may, on sort of current events, and again, just appreciate your time here. So, just a couple of hours ago, President Obama held a brief, or made an announcement about the precision medicine initiative that he proposed, and that is being spearheaded by members of Congress. He sort of talked about background, saying the number that I think we've heard a number of different places, that for every dollar that was invested in the Human Genome Project, that's now returned something, by some estimates, $147 in the economy. And I know there is some debate about how those numbers were developed. But then also, really encouraging entrepreneurs and NPOs, nonprofits, to make tools that help both scientists and individuals and patients. So for the individuals, get better access to their information and to understand it. So with that as the background, there was responses on both sides. I saw some people saying this just is kind of a rehash of a lot of things that we've been hearing for the last 10 or 15 years, and other people were really excited. So I'm curious to know what you think about this new initiative, where you'd like to see it go. Are you hopeful? What can we look forward to?
It seems like a drop in the bucket. So I'm not sure that $250 million gets us very far with the scale of that problem. We do. So my background's physics. It's measurement. We do need to measure everything better. We need better DNA sequencing. Our DNA sequencing is pretty good, but we could have lower error, faster, higher throughput instruments. That would be great. We need to do better on metabolomics. We need to do better on proteomics. We need to do better on everything. And I'm just not sure that phrasing that as precision or personalized medicine, or however it gets spun, is the right way to approach that problem. For this amount of money, quite frankly, I would rather see startup spaces get funded in 50 or 100 cities around the country. I'd rather see that the U.S. government lead on developing a space where people can do things safely and securely, and where there can be engagement both on the commercial front and on the government front, with people who want to, the governmental front, with people who want to play with biology, with startups that want to get going, with people who have ideas about technology or just science that they want to pursue and don't have access to at the moment, don't have access to the infrastructure. I think that a few $1 million here and there in those kinds of settings would do a lot for education and startup activity, and that we'd be further sooner through that kind of investment than we would by spending more money on more NIH-style projects.
Fair enough. Okay. Well, thanks so much for your time. Really appreciate it on behalf of the PLOS Synthetic Biology community. We really appreciate you talking with us today. Any final thoughts? Anything else you'd like to add?
No, thanks for having me on. I'm happy to do it again, and thanks for taking the time.
Great, thanks so much. And for everyone watching, this will be archived on YouTube. And again, Dr. Carlson can be found at synthesis.cc and on Twitter at Rob_Carlson. And thanks so much. Take care.
Bye-bye.